In this lesson, we're going to take a look at some of the terms we use in science, some of the units we measure with. You guys have already done all this in lab. We just want to formalize it and get it in your notes. So first, we said science was based on observation. Well, what's an observation? An observation is information collected with your senses, and it can be quantitative or qualitative. Now, a quality is something that you describe, and a quantity is something that you measure or count. So when we go through these different versions of observations, they're both valuable and they're both helpful, but we have to keep track of them in different ways. Qualitative observations describe things. We use adjectives. We can say smooth. We can talk about colors. We can talk about texture. A whole lot going on there. Quantitative things are countable or measurable. So you use a meter stick and you can get how long something is. You can count the number of things that are there, and you could measure mass. Any of those things that have numbers are quantitative. Now, don't confuse observations with inferences. Down over here, we have this diagram that shows some tracks going this way and another set of tracks coming this way, and then a jumbled up mess, and then they all trail off. Except they don't all trail off, right? There's different things going on there. An observation that I make is something that nobody can argue with, right? It's a fact. I can measure it. I can count it. It's the way things are. An inference is a story that we use to explain it. So if we looked at that, we would look, two things got together, looks like they fought, and the big one got eaten, or ate the little one and walked away. None of that's an observation. The observation is the things that we can measure or the things that we can describe. So we can say there are two sets of footprints. We can even notice that the footprints get further apart. And we can say things like two sets enter this mess and one set leave. But that's kind of it. We can't tell what happened. We're not there, right? So the inference that the big one started running, like that's what it means, right? If we start running, our steps get longer. Well, maybe some of those footsteps got washed away. We don't actually know what happened. We weren't there. So don't make an inference and mistake it for an observation. Make sure that the things that you're assuming to be true are in fact observably true, or it could throw off your results. Now, speaking of, we do have scientific theories that are true, but they're not proven. It's a well-tested explanation for a series of observations. So when we're trying to explain something that we see in nature, we do lots and lots of tests, and we come up with a theory that could explain why things are the way they are. They are never proved, but they can grow stronger as they predict more things and more tests are done. But if a theory doesn't match reality, then the theory has to change. And that's okay. Now, a theory is not a hypothesis or an idea or a thought. So when we use the term theory in science, we're using it differently than it is used in everyday common usage. So some major examples of theories, we have the theory of kinetic theory, or the theory that all matter is made up of particles in constant random motion. Changing that motion changes the property of the matter. Cell theory gives us the basic unit of life and how life adapts and changes and reproduces. And Big Bang theory tells us how the universe might have come into existence. So those are major scientific theories. Scientific laws just state this is the way things are. So it says every time we've tried this, this is how it's worked out. So the relationship you guys found in lab where the mass doesn't affect the speed of a pendulum, or the angle doesn't really affect the speed of a pendulum, those are true, and the length does. And there's actually a mathematical relationship between length and gravity that'll tell us the period of a pendulum. And it's a scientific law. It does not explain why it's the way it is. It just says when we have a pendulum that's this long, this is how fast it will swing in this gravitational field. So besides the pendulum, some other examples: law of inertia, which is Newton's first law, right? An object's velocity remains constant unless an unbalanced force acts on it. Bernoulli's principle, which tells us about the speed of air and the pressure it can exert, or a fluid. And the law of conservation of energy. Energy can't be created or destroyed. The faster a fluid moves, the less pressure it exerts, and an object's velocity remains constant unless acted on by an unbalanced force. Those are three laws. They don't explain anything about why that's the way things are. It just says that's the way things are. Now, we can model nature to help us see these laws, help us discover these laws, help us test these laws, help develop theories. And so they simplify complicated or hard to observe phenomena. Like looking at an atom is actually really hard to do, but we can model an atom with point particles and try to understand what's going on there. And they can inspire new questions and experiments. But don't confuse models with reality. So sometimes we'll be talking about the models of atoms in here, and we'll talk about how electrons are orbiting the nucleus, and we put them in little energy levels that we draw as circles. Well, they're not circles. The electrons aren't moving in orbital paths like that. So we've got to be careful about using the model to help us understand and actually thinking that that's the way things are. So models are useful tools, but remember, they're not reality. Now, I said an observation could be a quantitative measurement, so let's talk a little bit more about that. We will measure three main dimensions, and by dimensions, I mean quantities or different things. So we're going to measure mass, which is the amount of matter in an object. We'll measure length, which is the distance between points, and we'll measure time, and then we'll compare units like mass to volume, and volume is three lengths combined. Mass to volume is density, right? So we'll get some units that are combined, but they're all based off of these three dimensions. Mass, the amount of matter in an object measured in grams or kilograms. Usually we're going to measure in kilograms, but for small things we'll measure in grams. Length, like I said, distance between points, we'll measure that in centimeters or meters. You guys were already doing that. Length of your pendulum, you guys measured in centimeters. Longer distances, we'll use meters. Time, which is an ordering of events, you guys were measuring time already, and of course we do that in seconds. Now remember, when you make a measurement, all of your measurements include a number and a unit. If you don't give me a unit, I don't know what you mean. Now, how big the measurement is, that's the number, tells magnitude, which is how much, and the unit tells me what dimension is being measured, and it allows us to compare it to a standard, right? If I said something is 17 papers long, that wouldn't mean anything because a paper is not a standard unit. But if I say 17 centimeters, we know how long a centimeter is. It is a standard unit. We could use inches, it's a standard unit, but it's not an internationally standard unit. Centimeters, meters, kilograms, grams, those are international standards. So we can communicate around the globe using the SI unit.